Yeah, so this might be a little overwhelming already since I've written a lot on the board, but yeah, you might want to grab your popcorn for this one. Let's go step by step though. So, alternating series test. This is not going to be super intuitive. This is going to be more of a rigorous proof because it's not a very intuitive thing. But the alternating series test, if you know what an alternating series is, it's when this can be written in the form of this, where b of n is a series, and it's multiplied by negative 1 to the n or negative 1 to the n plus 1. I want to start it at 1 and do n plus 1, just because it's a little easier for this work to just like prove itself. If you've made some slight adjustments, you would be able to switch it around, but I'd rather have it like this. So the conditions we need for our proof, or for alternating series, is that b of n is positive, is always decreasing, and as it approaches infinity, it equals 0. So it doesn't necessarily have to converge. But if those things are true, then it will definitely converge. It might not always need to be positive, but I just want to put it in there to make this a little cleaner. Um, so if those are true, then b of n minus b of n plus 1 is always going to be greater than 0. Uh, and let's just define S of n as a partial sum of a. So if if this is true, then what we can say is, oh, this S of 2 is a positive number. Well, then S of 4 is this S of 2 times another smaller positive number. And then we just keep going that. So if we keep adding positive numbers, what we're saying is that as S of 2n, the even partial sums, so like let's just call it S of 2n, all of these, so they're all going to be increasing as S, or not all of them, but S of 2n is going to be increasing. It's always increasing because you're always adding a small positive number to them. So let's say the even the in like the last even partial sum is going to be the biggest one, and it's going to always increase. But over here, let's describe it in another way. Let's add all of these up. So I've written them out as S2 and then S2 plus that, S6 plus that. Well, the full form in one line would be S of 2n equals B1 and then this, and then B1 and this. But if we just put the parentheses in the right place, what we find is what we find is that we are adding these things. So these things, based on this information, will always be negative numbers. So B1, and then you add this negative amount, and then you add this negative amount. So this is if we if we start at B1, it's decreasing from B1. So what we know is that this series is always increasing as you add more terms to the n, but it cannot be bigger than B1. And from an intuitive level, that should make sense that by stating those two things, S of 2n must converge to a finite value. So the idea is, oh, I can't be bigger than, let's say, some number 8. But if I'm always increasing and I can't be bigger than 8, I will eventually reach 8 and then stop. Um, and if we go to infinity, you don't really stop, but at infinity, stopping stopping isn't a rigorous term, but essentially we go all the way up to our upper bound, and that's where we stop because we're always increasing, and then we reach an upper bound. So what this tells us is that for an alternating series under these conditions, if the final term, if our infinite term is supposedly even, then we'd get the sum SE for sum even, because we've explained that it's finite. It would be less than B1. Now, let's think about it in terms of our final term being odd. If our final term is odd, then this would be the same as just looking at, oh, what's our final even sum, and then adding our odd sum. Well, if we do that, you know how to take limits. This one would be our S even. And then this one, since we've said that the limit of b of n approaching infinity is 0, the last odd term is also going to be 0. So we've shown that regardless of whether our final term is even or odd, it converges to the same sum. So under these conditions, this converges. This should also make it clear why the alternating series error bound makes sense. Because we've shown that this sum is, or we've shown that these partial sums, each one is slightly decreasing from b1. So b1 is the maximum value it can be and for each subsequent term, it'll have to be less than the next unused term. It'll have to be less than the next unused term for these additions to make sense, right? Since since you're bounded at b1, it must be less than b1, and then say you go to b4 or you finish at b3. Well, it must, or you have b1 minus b2. Well, the remainder must be less than b3 because everything after here is less than b3. The same way everything after here is less than b1. So it should also explain to you the alternating series error bound. That might have been confusing because I ran out of space, but I'll let you take this in for a bit because it's a bit much. There's a lot of stuff on here, and it's an actual proof and not just me rambling. But I'll erase this side of the board so I can explain error bound a little more clearly. So we have our sum. We've proved that this is just our sum. So I'm actually going to not call it sum even anymore. I'm just going to call it S. So our sum equals b1 minus b2 plus b3 minus b4 plus b5 minus ... plus. So see, we have this sum, but we know that this is negative, and then we know that I need to put the plus sign there. We know that that's negative, and then we know that that's negative based on the thing that I just erased. I was very smart in erasing that. So we know that these two are negative based on what I had on the board around here before. And if those are negative, then what that means is that the sum minus b1 is, or what that means is that b1 is greater than the sum minus b1. So b1 is now so this is weird right now because this is awkward because it's our partial sum, but we're removing this one instead of the last term, which is what we usually do for remainders. But this idea holds true for any of these values if you just rearrange the parentheses accordingly. Say we have, say we want so we have s minus s3. That's our remainder, so we're looking at 4. Well, that should be this minus, and that's b1 plus b2 minus b3. So these all cancel out. Now that equals negative b4 plus b5 minus ... plus all the way to infinity. But what we see right here is that this is now the largest absolute value in the series, as shown multiple times. The first one will be the largest absolute value, as these will all be smaller. And what we know is that b3, at least, yeah. What we know is that b4 is now the biggest thing in this entire thing. b4's absolute value is larger than any other thing. So, and we know that if we arrange the parentheses correctly and not like an idiot, what we can say is, b4, negative b4, and then you add b5, and then you subtract b6. So now you keep going from b4, and now you keep decreasing. So what we can say is that the absolute value of b4 is the largest positive number we can take from this equation. So what we say is that this must be true. And that's why the alternating series error bound makes sense. I hope I explained that well. It was a little messy. I didn't really rehearse this, obviously, but if we take the absolute value of here, we do that, and or I guess I probably shouldn't have put the signs there. So we know that, but because it gets tricky with the signs, you just say, oh, absolute value of b4 is the biggest positive thing, and it decreases from there. So the actual sum must be less than or equal to the biggest number there. If you know. So that's how alternating series error works. I don't think I'll explain Taylor's theorem and Lagrange error bound because those are even more confusing. And I'm pretty proud of myself for this explanation. I hope you're proud of me because it will make absolutely no sense if I messed up a bunch. Yeah.